This lesson is going to focus on recursive type of sequences and what the recursive equation is for the arithmetic and geometric sequence that we've already been working with. So when you write a recursive equation, what you do is you're essentially just describing what you're doing to the very previous term to get the next term. That means this is a little different than the explicit equation that we had already explored for arithmetic and geometric sequences. So the benefits of the explicit one is that we could use it to find any number. You saw that over the last couple of lessons. But for the recursive, it's really more just telling you exactly what you would do to the term right before to get the very next term. So let's define a couple of things, because you're going to see in both of these equations you have something that is labeled a sub n minus 1 and then a sub n. So in a sequence, right, coming in from this side and then going on to the next, those two are essentially describing two terms that are right next to each other, and a sub n minus 1 is simply the previous term that comes before the a sub n, which is just always the next term in the sequence. So although this looks a little different and maybe a little intimidating, it really isn't, because if I read this and understand what's happening, all this is telling me, for example, for the arithmetic, is that each new term in the sequence is always equal to the term right before it plus the common difference. That's all that says. Okay, the recursive equation for the geometric says that each new term in the sequence is just going to be the one right before it times the common ratio. So whenever you spotted a pattern, you know, let's say that you were saying you started at 5 and you're going up by 2, so you're doing 5, 7, 9, 11. If you looked at it and say, oh, they're always adding 2 each time, well, that's essentially your recursive equation. You're saying they're always taking the previous term, adding 2 to get the next term. You just gave the recursive version or the recursive equation of that. So again, in both of these equations, this is the previous or right before, and this is the next term. And so it's just an equation that describes what's happening to the very next term based on the term right before it. That's it. It is great for describing the pattern. It is not great for predicting sort of further down. So if all you're wanting to do is describe what a pattern is happening, the recursive is very helpful for that. If you really need to predict then what is going to be the 40th term or the 50th term, then you really want to use the recursive formula that we had already explored. The explicit formula that we had already explored in the previous lessons. That's the one that's going to help you predict further numbers. All right, let's just practice reading and using the recursive version of arithmetics and geometric sequences. So let's start here with number 1. And they tell us here to write the first 6 terms in the sequence and then graph it on the grid here. So if you look, what they're telling me is, they're telling me the first term in the sequence, so I know what to start on. So here a sub 1 is negative 2, so that's already filled in. And then in the next line, they tell me that each new term is always going to be equal to negative 2 times the previous term. Okay, so what that means is that if I started at negative 2, so a sub 1 is just negative 2, then the next term in the sequence, this is what this right here is telling me, the next term in the sequence is simply going to be negative 2 times the term right before it. Okay, and so that's the pattern, and that would give me 4, so then the next term would be 4. Okay. And then for the next term, according to this formula, this next term is just going to be equal, so next term is going to be equal to negative 2 times whatever the previous term, the term right before, which would be my 4 here. And that would be negative 8. So the third term here is negative 8. That's all it is, right? So as long as we have that recursive version, I'm going to zoom in a little bit here, it just tells us what am I going to do to this just previous number to get the very next number. So as long as that's my rule, I know that I can find the next term in this sequence by just taking negative 8 and multiplying it by -2. So if I do -8 times -2, I get 16. Okay, so let's finish that out. It says find the first 6 terms. So we've already done 4 of them. I know that I can find my next term in the sequence by taking that 16 and multiplying it by -2. And I'll get -32 there. And then last but not least, to find the next term in the sequence, I know that I just multiply by -2 again. So really not very different. It's just telling you it's a different way to write an equation that describes how you're going to get the very next term based on the previous. What are they doing to this previous term to get the next one? What are they doing to this to get the next one? And you're just describing that as an equation. Okay. And then in addition to doing that, they also wanted us to graph here. So let's go ahead and do that. We are graphing the first 6 terms. So as far as our x-axis is concerned, we can stay here on the positive side of things. But I do need positives and negatives. So I'm thinking, and pretty large numbers. I've got to be strategic about that. Okay, so this is going to be the first term, the second term, the third, the fourth, the fifth, and the sixth term. And then I need to get all the way up to 60, so I probably need to go up to about 80 or something. So maybe I'll go up by 20s here. So this is 20, 40, 60, 80. That should be good. And then on the bottom here, this would be -20 and -40. All right. So let's take a look. We've got the very first term is a -2, so that's going to be very, very close to the x-axis here. And then the second term is a +4. It's a little bit further out. Then a -8, maybe about right here. They're still really close to the axis here. And then the fourth term is a 16. Now we're looking at maybe something more like there. We're just estimating these. Notice it doesn't have to be perfect or exact. You just have to do a nice educated job here. -32, maybe about right there. And then that 64 is going to be about right up there. Okay, there's your graph. You can see that these, again, this one was ageometric, so it flips back and forth. All right, so that is how we work with a recursive. It just gives us the pattern. It really is great for extending on, forward, but it's not necessarily good for predicting numbers that are way down the line. All right, let's try number 3 here. Number 3 is an arithmetic version. So if we look here, we're starting on the number 14, and what they're describing for us is that each new term is always just going to be the previous term minus 4. Okay, so if this first term is 14, to get this very next term, all I do is I take that 14, I insert it here, and I take 4 away to find what this new one is. So then I would get 10. So this term would be 10. And then to get the next term, I just take that 10, take away 4, according to my recursive, and that'll give me the next term in the sequence. So there's my 6. So again, you can start to see that it's really the same idea. I take my 6 here, that was my previous term. I take 4 away. That'll give me the next term in the sequence, and that is a 2. And then if we take 2, you know the drill here. We'll finish this out, and then -2. We take 4 from that, oops, equals, and we get -6. So that was a -2 and a -6. There is our equation. It is arithmetic. The pattern was always each new term is just the previous term minus 4, and then we can go ahead and graph that. And I'm going to graph that just a little bit faster here if you want to pause your video and check out the graph. Okay, so we have our grid here, and we know that the first term was 14, so a couple of these might fall off just a tiny bit, and that is okay. So 14 would be 12, 14 right about up here. And then the next term was a 10. The second term was a 10 here. And then the third term was a 6. Fourth term was a 2. Then a -2. and then a negative 6. There's your graph. And it is, as predicted, a straight line. All right, so that's how you use it. It's really just predicting as a way to, and mathematically describe what the pattern is. That's all it is. So here, let's write a recursive rule for the sequence. So now they're giving us a sequence, and we want to find the recursive rule here. First of all, let's always identify what number we're starting at. That's always important. So let's go ahead and identify our first term in the sequence is 324. Okay, and then all we need to do is then spot what the pattern here is. We could check to see if it's geometric or algebraic. The fact that this difference is so much different than that tells me this is probably geometric, but let's check. So 108 divided by 324 gives me 1/3. And then if I do 36 divided by 108, I get 1/3. If I do 12, I already know that one. 12 divided by 36 is going to be 1/3. So we have a sequence that starts at 324 and has a common ratio of 1/3. So remember, since this one is geometric, our formula, our recursive formula or equation is that each new term is just that common ratio times the value right before it. That's the recursive geometric. So all we do then is say, okay, we're starting at 324. Go ahead and establish that. And every new term in this sequence is just going to be 1/3 times the value right before it in the sequence. And that is our recursive. That's simple. Okay. Try number 6. On number 6, I can see here that they're adding 5 every time. They're increasing this by 5. That makes that arithmetic. So let's review quickly here. We know that each new term in an arithmetic is always the previous term plus or minus that common difference, depending if it's positive or negative. And this has a first term of 9 and a common difference of 5. That's what they're adding every time here. So I could say, okay, they're starting at 9, and every new term is simply the previous term plus 5. And that's your recursive description of the pattern. That's it. Okay. Same thing here. We don't necessarily need to do more than just a couple of these, except instead of in a table format, they're giving it to you in more of the traditional sequence here. But here we want to definitely identify our first term as 3,125. The way that this is decreasing so quickly, I'm thinking it's geometric, so let's find out. If we do 625 divided by 3,125, it's 0.2 or 1/5. And if I do 125 divided by the 625, I get the same. 25 divided by that is the same. So it is 0.2 or 1/5. You can write it either way. And then we use the recursive, since that's what they're asking us for here, that says each new term is just that our common ratio times the term right before it. So let's go ahead and write that. Our first term was 3,125, and every new term is just going to be 1/5 of the term just before it, of the previous term. Okay. Let's try one more here. If we look for a pattern, this increases by 6, then it increases by 6 again, then 19 plus 6 is 25. This one's pretty easy to see just at a glance that it is arithmetic. And so again, if it's an arithmetic, then our formula for that is always the new term is just the one right before it, plus or minus that common difference. I say plus, but it could be negative, right? And then we know it would be decreasing. But in this case, our first term is 7. And our common difference is 6. So we could just write this as first term is 7, and every new term after that will always just be the one right before it plus the 6. So every new term will be the previous term plus 6. That's how we're going to find each term in the sequence. Okay, so that is writing a recursive. Let's flip that over. You could even write a recursive equation from a graph. So we've done it from a table, we've done it from sequences, It wouldn't be any different to write it from a graph. Again, it's really just a more formal way of describing the pattern. So let's take a look at number 10. Number 10 here, just based on this graph, it looks kind of pretty linear, and I can put a straight edge to this and confirm that. But it's always also just really smart to check in with the values and see, oh, look, they're decreasing by 3 every time. 15, 12, 9, 6, 3. This is definitely arithmetic. So as long as we can identify our first term and the common difference, we are in business here. So our first term in the sequence is a 15, since that's paired up with a 1. And our common difference is a decrease of 3. So that's a negative 3 here. So to write the recursive, we would say the very first term is 15, and every term after that is simply the previous term minus 3. Yes, folks, it is that simple. How nice, right? All right, let's try this one here. This one looks a little bit more interesting. Definitely not a line. You've got a very sharp curve coming in here. Let's look at the difference here. Our first term was 20. And if it helps, by the way, you can definitely list out your sequence if you find that you work better off of that. So we could say, you know what, my first term is 20. My second term is 4. My third term is 4/5. The fourth term is 4 over 25. My fifth term is 4 over 125. Just based on that, I'm pretty sure this has a multiplicative relationship, but let's check to be sure. 4 divided by 20 is 0.2, or again 1/5. And then if I do the next one, which is 4/5 divided by, oh, I should probably do that in a parentheses, 4/5 divided by 4, I get exactly the same thing, and I could do it again and say 4/25 divided by the 4/5. Need to insert a parentheses there. There we go. So we definitely have a common ratio here, and it is 0.2 or 1/5. So we can establish, all right, our sequence starts at 20, and our common ratio is 1/5 or 0.2, 2/10, and that's enough information. All we have to say is our sequence starts at 20, and every new term is simply 1/5 times the one right before it. There it is. Okay, so I think we hopefully feel really comfortable writing the recursive equation for arithmetics and sequences. So what I want to do now is for a moment practice simply being able to flip back and forth between the explicit rule that we learned in the previous few lessons and changing it to the recursive, or vice versa. Okay, so let's talk about that. Okay, remember the explicit rule is the one that does help us predict further down the line, and it's on your notes for lessons 4.7 and 6.5. And what we want to do is take this current explicit here and then use it, take this current recursive and use it to write the explicit. So write the explicit for the recursive. So we really want to go in this direction, actually. But let's go ahead and do that on number 12. So on number 12, again, this is a recursive equation, so it's just explaining to me what the pattern is in the sequence. It's telling me we started at 4, and each new term in the sequence is equal to 3 times the previous term. That is enough information for me to know that this is geometric. Okay, and therefore, if I'm going to write the explicit equation for a geometric, that looks like this. We did this last time. Okay, that's the explicit formula. It lets me fill in the first term and the common ratio and then use it to predict any other value down the line. Okay, so as long as I can, from this information, pick out what the first term is and what the common ratio is, I have all the ingredients I need. Okay, so according to this, my first term is 4. My common ratio is going to be in my recursive what they're multiplying the previous term by, which is 3. So this is telling me each new term is equal to 3 times the previous, so that 3 is your common ratio, is what you're multiplying by. and then I can just write my explicit formula. So my explicit formula here would be that I can find any nth term by making sure I take the first term, which is 4, and multiply it by the common ratio, 3, raised to the n minus 1. That, if that looks familiar, but that's because that's the explicit rule for geometrics, which you had already learned. And now I can find the 100th term if I want. You know, I can just plug in 100 here and 100 here and then evaluate that, and it'll tell me what the 100th term or any term I want. Okay, let's do that for number 13. I can see here, based on this recursive, that I'm starting at 6, and each new one is just the previous one plus 11. So that plus 11 tells me that this is arithmetic. And the arithmetic explicit that we want to write is always the first term plus that common difference times that n minus 1, and then we do simplify that one, don't forget. So as long as I know the first term, which they told me is 6, and the common difference, which I can see here is 11, that's what they're adding every time, then I can write this explicit. So it's going to be, I can find any term as long as I know I'm starting at 6 and then adding 11 n minus 1 times. And remember, we simplify this one, so we'll distribute that 11. We'll do 11 times n and 11 times that negative 1. And then we'll combine our like terms. So the final arithmetic explicit here would be 11n minus 5. And then I could use that to find any term in that sequence that my heart desires. All right, let's talk about going in the other direction. What if we're going, if we want to write the recursive given the explicit, okay? So this guy right here is our explicit arithmetic. Looks just like this one that we just did. And if we can pick out, again, what that common difference is, that's primarily what I need here. And that's always essentially connected to your n. It is your slope, if you think of this in a linear type of format, right? So we know just by looking at this that the common difference, the value that this is increasing by every time, is 6. And then I think it's also really important that we still find the first term. So we still want to be able to always start off and say, hey, the first term of the sequence was such and such. So to do that, we'll just plug in n equals 1. So to find the first term in the sequence, we make n equals 1, and we solve for that. And that 6 times 1 is 6, plus 2 is 8. So according to this, the first term in the sequence is 8, and the common difference is 6. And I can now write my recursive. Well, all I have to do is say, hey, our sequence starts at 8, and then every new term in the sequence is just the one right before it, plus 6. Sorry. I got a little messy there. So plus 6. And that would be your recursive for that explicit. Let's do the same on number 16. Okay. We can see right away it has an exponent. It has a geometric format to it. So this is a geometric equation. I still want to be able to identify what is the common ratio, which is always our multiplier here. So in this case, it's -3. And what is the first term in the sequence, which means we'll have to plug in a 1 here. Okay, so if I want to find the first term in the sequence, I just evaluate this for when n is 1. But 1 minus 1 is 0, and anything to the 0 power is 1. So our first term in the sequence here must be a 1. But those are the only ingredients I needed to write my recursive, because now I can say, oh, so this sequence starts at 1, and the pattern is going to be that every new term is just going to be -3 times the term right before it. It's just describing the pattern. And there you go. And that really wraps up our conversation about arithmetic and geometric sequences and writing the recursive equation for these. We're going to explore this last section, which is kind of fun. They're not arithmetic or geometric. They have other patterns. So I invite you to check that out and see if you can figure out what the pattern is. It's going to be recursive, so think of it in terms of what are they doing to the previous terms to get the next terms, and then we'll see how that went in class.